Welcome to the O-Level Chemistry lecture series. There are some recommended additional practices which you may try after you finish this set of lecture series. So for today's topic, it is on electrolysis. To begin with this lesson, please have ready on hand the notes on electrolysis. The lessons will be delivered through PowerPoint, which will closely mirror the flow of the notes. So if you do not have a copy of the notes, please obtain them from Melvin at the photocopy shop. Alright, let's begin. So what is electrolysis? Electrolysis is the decomposition of a compound by electricity. And the compound is usually an ionic compound in the molten or aqueous state. So for example, if I have NaCl, sodium chloride as you know it, this is the solid state. You can't do electrolysis with this. Why? Because the ions are fixed in a crystal lattice. They are not mobile, they cannot move, they cannot carry a charge. NaCl, molten, liquid state. In the molten state, you get Na plus and Cl minus ions. These ions are now free to move and they can carry a charge, which will allow electrolysis to take place. NaCl aqueous also has ions present, similar to Na plus, Cl minus, but now they are in the AQ state. Aqueous, AQ for water. So the diagram you see on the slide now is a very simple electrolytic cell. So there are a few parts in the electrolytic cell which you will need to know. So first of all, you need a power source. Because if you recall the definition, it is the decomposition of a compound by electricity. So the power source provides this electricity. There are two electrodes here. One is called the cathode and one is called the anode. So they are named this way because the cathode attracts the cations. Cations, if you recall, are positively charged ions and they are attracted to the cathode because the cathode is connected to the negative terminal of the battery or the power source in this case. The anode attracts the anion. The anion is negatively charged. So being negatively charged, you'll be attracted to the positive terminal of the power source. Last but not least, you have this solution inside, which is called the electrolyte. The electrolyte is basically something which allows the conduction of current to take place within the electrolytic cell. So as I summarized earlier, the cathode is connected to the negative terminal of the power source. Cations will migrate to the cathode because they are positively charged. And reduction occurs to the cathode. Later on we will see more about this. The anode attracts anions because it is connected to the positive terminal of the power source. And oxidation occurs at the anode. Later on we will cover more of this as well. But just to let you know first, you can remember the oxidation or reduction processes happening at the anode or cathode with this simple AOCR. Anode for oxidation, cathode for reduction. The electrolyte, as I mentioned, conducts electricity because of the presence of free moving ions. These free moving ions can be in the aqueous state or can be in the liquid state. And to do this, they are usually ionic compounds. And because there's current flowing through the electrolyte, at the end of the day, the electrolyte is usually decomposed. That means it breaks down and it forms other substances. So let's take a look at this diagram here. You notice that the current flow is as such. Cations migrate to the cathode. They receive electrons from the power source, and as a result, they are reduced. So let's take, for example, the cation in this case is, let's say it is Cu2+. So Cu2+ receives electrons and it becomes reduced to give you copper solid. And this copper will be deposited around the electrode here. Similarly, at the anions, the anion migrates to the anode. So let's have an example, OH minus, an anion. So when it moves to the anode, it loses electrons to the power source, and as a result it is oxidized. So OH minus, most of the time it is oxidized to oxygen gas. Later on we'll cover more about this as well. So let's do a quick pre-check first. Pause the video now to attempt the pre-check. Continue the video once you are done. The correct answer for this question is B, for mercury and dilute hydrochloric acid. Why? Because for the bulb to light up, there must be a current flow going through the entire electric circuit. So to do this, the two solutions here, or the two electrolytes here, must be able to conduct electricity. So if you look through all the options here, mercury it can conduct because mercury is essentially a metal. So being a metal, it contains delocalized mobile valence electrons which can conduct electricity. Dilute HCl, dilute means it is in the aqueous state. It dissociates to give you H plus and Cl minus ions. So these two ions can also migrate to the electrodes and they give rise to the flow of electric current. So the correct answer is B. Okay, so let's move on to the topic of electrolysis of substances. So there are two areas you will need to know. First is the electrolysis of molten binary compounds. What are binary compounds? Later on we will cover. And the electrolysis of aqueous electrolytes means it contains water. It is dissolved in water. And for aqueous electrolytes, the electrolysis is a bit special because it depends on a few factors, one of which is the nature of the electrodes, inert and reactive. As the name already tells you, the reactive one would probably play a part in the reaction. The inert one would probably not do anything during the reaction. So let's take a look at the first area first, the simple one, the molten binary compounds. So what is a binary compound? A binary compound is something which is made up of two elements, usually a metal cation and a non-metal anion. For example, a very simple one is again NaCl. Na and Cl. So Na is one element, Cl is one element. This is the metal part, this is the non-metal part. And if you recall, metal, non-metals, they come together usually to form ionic compounds. So why molten? Because if you recall, NaCl is arranged in the crystal lattice structure. So let's say this is the diagram of NaCl, and the circle here represents Cl minus, the dot represents Na plus. In solid state, they are arranged at fixed positions in the lattice, so they are not free to move, they cannot conduct electricity. But in the liquid state, all these electrostatic forces of attraction between the Na plus and Cl minus ions are broken and they are free to move. Take note, liquid state means that they are melted. The state changes are solid, liquid, gas. So solid to liquid is melting. It is not, I must reinforce this, it is not dissolving. When you dissolve NaCl, probably in water, it will be NaCl bracket AQ. This case, it is NaCl bracket L. L for liquid because it is molten. So this is a very simple setup for the electrolysis of molten sodium chloride. If you see there's a heat source present, the heat source is to melt the sodium chloride. There's a power source and there are the electrodes here again. You may be required to draw this diagram, so take a closer look. Try to remember the critical parts, the heat, power source, the electrodes. Alright, so how do we go about identifying what ions are discharged at the various electrodes? Discharge means it comes out of the electrolyte. So very simple, it's a very simple process to do this. First of all, we identify what is the electrolyte first. In this case, it is NaCl. So as I mentioned before, must be in the liquid or molten state. Otherwise, the ions are not free to move. So once we identify what is this electrolyte NaCl, we can very quickly know what are the ions present, Na plus and Cl minus. And because this is a binary compound, it means there are only two elements. And one of it is positively charged, one of it is negatively charged. So if you recall the electrolytic cell, you have one which is, you have an electrode connected to the positive terminal of the power source, you have an electrode connected to the negative terminal of the power source. It means that the Na plus ions will migrate here and the Cl minus ions will migrate here. And because the cation ions migrate here, this is called the cathode and this is called the anode. Okay, so the next thing we need to do is to identify what electrodes are used. Most of the time they use carbon. Carbon is also called graphite electrodes, if you recall. Graphite is an allotrope of carbon. The other allotrope of carbon is diamond. Yes, correct. Diamond. So carbon is an inert electrode. It doesn't take part in the reaction, so we can ignore it in this case. Pretend it doesn't exist. It is just there to conduct the the current flow. Alright, so now what happens at the electrodes? So as you can see, this is the positive electrode, this is the negative electrode. Cl minus being negatively charged will be attracted to the positive electrode. So when they reach the positive electrode, it loses the electron. Take note, each Cl minus ion lose 1 electron. So each Cl minus loses 1 electron to give you Cl. To give you Cl atom first, and then two Cl atoms come together to give you chlorine gas. Okay? So overall, we can see that the Cl minus ions are oxidized because if you take a look here, the oxidation state for Cl minus here is -1. At the end of the day, it is 0 because it is an element. So this is an increase in oxidation state. So we say that Cl minus ions are oxidized. And because they form a gas, we say that they are discharged as chlorine gas. So during the electrolysis of molten sodium chloride, you would probably be able to see some greenish vapor coming out, and this greenish vapor would be chlorine gas. And if I link this back to QA, how do you check for the presence of chlorine gas? It would be with a damp blue litmus paper. So blue litmus paper will turn red and then it will be bleached. So this is a distinguishing test for chlorine gas under QA. Alright, let's move back to electrolysis. What happens at the negative electrode here? The negative electrode attracts the positively charged Na+. So this is also known as the cathode because it attracts the cation. So when the cation reaches the cathode, what happens? Each Na plus ion gains 1 electron. They gain 1 electron to form a sodium atom. So if you take a look here, Na plus to Na oxidation state is +1. End of the day is 0. So this is a reduction because it decreases. Take note of the state. It is in the liquid state. This is molten because the whole setup is still hot. It is hot to melt the NaCl. So at the end of the day, if we combine the two equations at the anode and cathode respectively, we call these two equations half equations. Half equations. Why? Because this is one half and this is the other half. They combine to give you the overall equation. Take note, you must balance out the electrons. There are 2 electrons in this case here. So on the left and right side, they must cancel out. So to get rid of the electrons, you have to multiply by 2 for the half equation occurring at the cathode. So end of the day, you have NaCl becoming Na and Cl2. Very simple. Alright, so now pause the video now to attempt the checkpoint. Continue with the video once you are done. Alright, so what you see here is an electrolysis tank used industrially to produce aluminium from aluminium oxide. Long time ago, this used to be in syllabus, but it is out now. But this still makes for an interesting question. So as you can see, if you analyze this question, there are a few things that are unique here. You notice that there's the electrode. The anode is actually here, 2 big blocks of graphite anode, and over here the graphite cathode lines the vessel. It lines the electrolytic vessel. So molten aluminum is here. So by its position at the bottom of the electrolysis tank, it means that molten aluminum is more dense, is denser than the stuff here. So it sinks and it is extracted from this point here. Okay, so let's attempt the questions. First of all, explain why the aluminum oxide ore has to be heated until molten. So Al2O3, ionic compound. Ionic compound, it means that the ions are fixed in their crystal lattice structure. So not free to move. So not free to move, it means that it cannot conduct electricity. So the bonds have to be broken. Hence, they need to be molten. Right, let's take a look at the answers. Did you get it right? The next part, constructing ionic equations for the reactions which take place at the electrodes. So again, there's the cathode and there's the anode. The cathode is where the cations go to, anode is where the anions go to. So by simple deduction, the cathode would attract the Al3 plus ions, the anode would attract the O2 minus ions. So what do we get? We get Al metal discharged at the cathode and O2 gas discharged at the anode. Take note, state symbols must always be written for ionic equations. Alright? Okay, so part C is quite simple, whether oxidation or reduction occurs at each of the electrodes. We know that at the cathode is reduction, at the anode is oxidation. Remember AOCR, anode oxidation, cathode reduction. Y plus 3 to 0 for aluminium, minus 2 to 0 for oxygen. The last question is I would say it's a special question. So carbon is an inert electrode. So being inert, it does not participate in the reaction, but then again, it must be replaced regularly. So why is this so? So if we take a look at the diagram, in order for the aluminium ore to be electrolyzed, it must be in this molten state, which means that temperatures are extremely high. So carbon, when temperatures are very high, what happens? So if you recall, carbon, high temperature, what is present? There is oxygen. The oxygen is produced at the anode. So anode is made of carbon, oxygen is present. End of the day, the oxygen would react with the carbon anode to give you carbon dioxide. So as the reaction proceeds, the anode gets smaller and smaller. Eventually, when it is too small to be useful, they have to be replaced. Okay, so that is for molten binary compounds. Let's move on to the electrolysis of aqueous electrolytes. This one is a bit tougher because there are 4 different factors which come to play, of which the electrodes also contribute a significant role. So let's take a look. Let's compare. Let's do a very simple comparison between a binary compound and aqueous compound. So in sodium chloride binary compound, electrolysis of NaCl molten versus NaClAq. What ions are present? We have Na plus and Cl minus. There are only 2 ions here, so it is very straightforward. Na plus goes to the cathode, Cl minus migrates to the anode, and it is discharged as chlorine gas, and this is sodium metal. But in the aqueous solutions, there are a bit more ions in play. So we have Na plus Aq, Cl minus Aq, and we have H plus and OH minus Aq. So where do the H plus and OH minus Aq ions come from? So we know that there's water present because this is an aqueous solution. So we also know that water can very partially dissociate to give you H plus and OH minus Aq ions. So it also means that whenever there's an Aq or aqueous solutions, there will always be H plus and OH minus ions present. So take note, when you are doing your analysis of solutions, if it is aqueous, you must bring in H plus and OH minus, and then you can compare. So now, which ions gets discharged? So remember, Na plus Aq, H plus Aq, Cl minus Aq, OH minus Aq. These 2 ions will migrate to the cathode. These 2 ions migrate to the anode. So which one is discharged? And in electrolysis, we say which one is preferentially discharged or gets a VIP treatment. So let's do a quick check. Na plus, H plus, which one do you think? Cl minus, OH minus, which one do you think? Okay, let's take a look. So for cations, the earlier topic was on metals, the reactivity of metals, and there was this thing, the topic called the reactivity series. So once again, the ion which is discharged, the cation which is discharged, depends on where it is in the reactivity series. The more reactive it is, the more reactive metal will form a less reactive ion. So being less reactive, it means that it will want to stay in the solution. It is less likely to be discharged. So if you look at this little series here, it is similar to the metal reactivity series, but in this case, you notice that these are all ions. K plus, Na plus, Ca2 plus. They are all just ions. Metal ions are almost always never discharged when you electrolyze an aqueous solution. Why? Because H plus will always be present whenever it is an aqueous solution. So if it is a solution of, let's say, zinc 2 plus and something else, there will be H plus present. H plus will be preferentially discharged. But if there are ions such as Cu2 plus, Ag plus, then these two ions will be preferentially discharged. So assuming a solution contains Cu2 plus, when all the Cu2 plus has been fully discharged, the next ion you will move on to will be H plus, because H plus is present in the aqueous solution. So as I mentioned earlier, metal ions are almost always never discharged in aqueous solutions. Almost always never, except for these two ions here. For anions, it is a bit more unique. The larger anions are more stable. Sulfate in particular is very stable, so it is always not discharged. And for the sulfate ion to be present, Aq, so notice Aq, it means that there will be the OH minus ion present as well. So just for your information, sulfate ion looks something like this. So you can see this is a huge anion versus OH, which is a small tiny anion. So OH minus will always be preferentially discharged. The smaller ions are more easily discharged, right? Okay, so the next thing is concentration. The concentrations can affect which ions are preferentially discharged. Why is that so? Later we'll analyze this a little bit deeper, but for now, let's take a quick look. Dilute aqueous NaCl versus concentrated aqueous NaCl. Sometimes concentrated NaCl is also known as brine, B-R-I-N-E, brine. So the con of Na plus is higher in brine, con of Cl minus is higher in brine, but take note they are still aqueous states. Why aqueous states? Because they are still dissolved in water. H plus OH minus largely will be the same because there's so much water that we don't take this into consideration. But let's take a look at what are the ions which are preferentially discharged at the electrodes. So for dilute NaCl, anode is OH minus, cathode is H plus. For concentrated NaCl, the anode is Cl minus, the cathode is still H plus. So why? Why is this so? Later on, we will go a bit deeper into this. So now move on to the nature of electrodes. Reactive electrodes participate in the reaction. Inert electrodes do not participate in the reaction. So these two, having a reactive electrode will result in a different reaction happening. So later on, we'll cover this as well under the electrolysis of copper 2 sulfate solution with copper electrodes. Okay, so let's do a quick analysis of the earlier part on dilute NaCl and concentrated NaCl. So there are 4 simple steps to follow here to determine what is discharged at the end of the day. Okay, so dilute NaCl, NaClAq, 4 steps. First step, we determine what are the ions present. Second step, we determine what is discharged at the cation, what is discharged at the cathode. The third step, we determine what is discharged at the anode, and then we combine 2 and 3 together to get the overall reaction. So let's start with the first one. So what are the ions present in electrolyte? So we know that NaClAq, it means that there will be Na plus, there will be Cl minus from NaCl, there's H plus from water, and there's OH minus from water. So now we move on to the next step, which is the cathode. So we determine what is the ion that is discharged at the cathode. So we know that the positively charged ions will migrate to the cathode because they are positively charged. Right? So Na plus and H plus ions will move to the cathode. And based on the series, let's take a look at the series. It's in one of the earlier slides. So Na plus is on the top, H plus is at the bottom. So ease of discharge increases. This is easier to discharge, easy. This is difficult. So H plus ion is preferentially discharged over Na plus. And at the cathode, the H plus will receive electrons to give you hydrogen gas. So this is a +1 to a 0. So this is also a reduction. Na plus ions remain in solution. The next one is the anode. N ions migrate to the anode. We now have Cl minus and OH minus. And again, if you recall, Cl minus, OH minus, this is sulfate. So ease of discharge increases down this series. So OH minus is preferentially discharged over Cl minus. And in this case, OH minus is discharged as water and oxygen gas. So we will actually see some bubbling around the anode. And if you look in your notes at the diagram, you will see that there's some gas collected in the tube above. The Cl minus will just remain in the solution. Okay? Yeah, so OH minus at the bottom, Cl minus at the top. So overall, you realize that this is actually the electrolysis of water. Okay, at the cathode, H plus is discharged. H plus is discharged as H2. At the anode, OH minus is discharged as oxygen gas and water. So if we combine the two half equations together, we actually get the electrolysis of water. Okay, it is similar to the electrolysis of water. Okay, so now if we take a step back and we think about the reaction, if this is the electrolysis of water, it means that as the reaction proceeds, the volume of water will decrease. So recall your mole concept. Concentration is equal to number of moles divided by volume. So we know the number of moles of NaCl do not change because Na plus and Cl minus ions are not discharged. So no change. But we know that the volume will decrease, which means that at the end of the day, the concentration of NaCl will actually increase. So as this increases, it affects what products are formed during electrolysis. So let's take a look. So now, after some time, it will be the electrolysis of concentrated aqueous sodium chloride, or what we can call brine. So analysis is still the same: ions, cation, anode, and then overall. So identify the ions, no change. Na plus, Cl minus, H plus, and OH minus, no change. But now this is a little bit different. So at the cathode, you still have Na plus and H plus ions. And if you recall, Na plus ions are almost never discharged. In fact, you can say that they are never discharged when they are in aqueous solutions because H plus is always present, and Na plus is so far away from H plus ion, right? So H plus will still be discharged, and it will be discharged as hydrogen gas. Okay, so this is a reduction. The anode is where the interesting thing happens. So once again, we have Cl minus and OH minus at migrating to the anode. And typically, we know that Cl minus and OH minus would be preferentially discharged. But in this case, because the concentration of Cl minus is much higher, and Cl minus and OH minus, they are actually pretty close together in the series. Pretty close, take a look. It's here versus here. They are pretty close in the series. It means that because the concentration of Cl minus has increased, there will be a lot more Cl minus around the electrodes, and by their properties, these properties will be taught to you in A-level chemistry, Cl minus will be preferentially discharged as chlorine gas. So in the earlier scenario, we have OH minus coming out as oxygen and water. This equation is not balanced. Please balance it yourself. In concentrated solutions, we have a different ion which is discharged, Cl minus. It comes out as chlorine gas. So chlorine gas will be collected at the anode. And if you recall, chlorine gas is a greenish yellow gas. OH minus will remain in solution. So at the end of the day, what do you get? You get H2 gas at the cathode, and you have Cl2 gas at the anode. Okay, so take a while to think about this, because questions usually involve asking you to compare between the products that are discharged for a dilute and a concentrated solution. Okay, so now let's move on to checkpoint 2. Pause the video now to attempt the checkpoint. Continue the video once you are done. Okay, so for checkpoint 2, you see a electrolytic cell here, and the electrolyte is concentrated HCl, and there are two gases that are collected here. Okay, there's a slight error in the notes, so please change the diagram here. It should be this, because the longer line represents the positively charged terminal, the shorter line represents the negative terminal. Okay, so let's move on to the question proper. So what are the names and formulas of all the ions present in the solution? It is HCl. So what ions are present? So what happens when each of these ions arrives at an electrode? So which one goes to which electrode? And what is the ionic equations for the reactions at the electrodes? So cation is H plus, anion is Cl minus and OH minus. So OH minus is from water. So what happens? The positively charged H plus ions migrates to the cathode, and it is reduced and discharged as hydrogen gas at the cathode. H plus gains electrons, give you H2 gas. Both Cl minus and OH minus migrates to the cathode. Okay, both migrates. But because this is concentrated HCl, it means that the con of Cl minus is actually much higher than OH minus. So as a result, Cl minus is preferentially discharged as Cl2 at the anode. So we have H2 gas and we have Cl2 gas. What gases are collected in the test tubes? It is quite simple. We ignore this diagram here. Take note of the charges, take note of the terminals. So positively charged terminal, Cl minus will be attracted here. Negatively charged terminal, H plus will be attracted here. This will give you hydrogen gas. This will give you chlorine gas. Right? So we have chlorine gas and we have hydrogen gas. And how do you identify them? Chlorine gas, yellow-green, pungent smell. It turns moist blue litmus paper red and then bleaches it. Remember to include the bleach part. The bleach part is a distinguishing characteristic. H2, very simple, it extinguishes a lighted splint with a pop sound. Alright, so now I have a bonus question for you. If you observe the diagram very closely, you will see that the H2 volume appears to be more than that of the Cl2 volume. Why is this so? So why is this so? Any idea? Okay, so if you think about this reaction, we have H2, H plus giving us H2, and we have Cl minus giving us Cl2. So effectively, to do this, this is the equation. So when we combine these two half equations together, what do we get? We get HCl giving us H2 plus Cl2. So the mole ratio is 2:1:1. So based on the mole ratio of 1:1, we should deduce that the volume of gas collected at each electrode should be the same. So why is it not the same in this case? This is because H2 gas is not soluble in water. Cl2 gas is soluble in water. So when the Cl2 gas is produced, what happens? It can dissolve in the water. It can dissolve in the water of the electrolyte. So as a result, because it dissolves, there's less gas, the water level will be a bit higher. So take note, sometimes the questions will ask you to draw in the water levels for the electrolytic cell. So if it's a gas which is soluble in water and you know that it is a 1:1 ratio, make sure that you draw the water level a bit higher for the gas which is soluble in water. Alright? Okay, last question is a very simple question. Why is steel not used for the anode? It's simply because steel contains iron, and iron will react with chlorine. Okay, the chlorine is produced at the anode. So once the chlorine is produced, it can straight away react with the iron in the steel anode. Take note. It is reacting with the iron in the steel anode. It is not reacting with the steel anode. The iron is in steel. Steel contains iron and carbon. So the carbon doesn't react. It is the iron which reacts with the chlorine gas that is produced. Let's move on to the next part, electrolysis of dilute sulfuric acid. So in this setup, if you observe very closely again, you will see that the volume here appears to be different. So let's analyze the question. So very easy, let's start again. ICAO. What are the ions present in electrolyte? So because this is dilute sulfuric acid, H2SO4 bracket AQ, you will have your H plus ions, you will have your SO4 2 minus ions from the acid, and you have H plus and OH minus from the water. So what is the ion that is discharged at the cathode? There is only one positively charged ion, in this case H plus, so you only have H2 gas discharged at the cathode. Again, this is a reduction reaction. At the anode, what happens? At the anode, there are now two ions at the anode, SO4 2 minus and OH minus. So both ions migrate to the anode, and if you recall the series, SO4 2 minus is way above, OH minus is way below. So OH minus will be preferentially discharged, and how is it discharged? It is discharged as O2 and water. So your sulfate remains in the solution. Okay, so way on top, way below. So overall, end of the day, what do you get? You again get the electrolysis of water to give you H2 gas and O2 gas. So based on this overall reaction, can you deduce something already? You see that the mole ratio of H2 and O2 is 2:1. 2:1. Right? So if you recall the earlier diagram, 2:1. Take note, 2:1. Let's go back a little bit. 2:1. This is 2 is to, it is almost 2:1. The volume of hydrogen gas collected is double that of the volume of oxygen gas. So based on this, if I give you a blank here, you should be able to fill in the polarity of the electrode. So O2 gas comes from OH minus, so OH minus must be attracted to the positive terminal of the power source. H2 gas comes from H plus must be attracted to the negative terminal of the power source. So end of the day, the overall reaction is this. This is the first half equation. This is the second half equation. We must cancel out the electrons on both sides. So we times 2 to the equation here, and we get H2O gives you H2 and O2. So only water decomposes in the electrolysis of dilute sulfuric acid. So now let's move on to checkpoint 3. Pause the video now to attempt this checkpoint. Continue the video once you are done. Checkpoint 3, very simple question here. You have dilute sulfuric acid as the electrolyte. You have carbon electrodes. So recall, carbon electrodes are inert electrodes. What is the other electrode? What is the nature of the other kind of electrodes called? Yep, correct. It is reactive electrodes. In this case, this is inert, not reactive, so it doesn't really play a part. You have your power source, and that's about it. You are passing a current through dilute sulfuric acid. So let's analyze this very simple question. What ions are present? H plus, SO4 2 minus, and OH minus. So what is the ionic equation for the reaction at each electrode? So H plus becomes H2 by gaining 2 electrons. This one occurs at the cathode. What about the OH minus? The OH minus loses electrons to give you water and oxygen gas, and 4 electrons at the anode. So these are the 2 ionic equations occurring at each electrode. So how do you test for oxygen gas? This is a very simple question. It is colorless, odorless. Take note, when you identify a gas, when you try to identify a gas, the color and smell must come out first. Color and smell, color and smell, and then you have the distinguishing test. Okay, the distinguishing test. So in this case, for oxygen, it relights a glowing splint, or you can say it rekindles a glowing splint. And this one, why is the volume of hydrogen collected twice that of the oxygen collected? So as mentioned earlier, overall reaction 2:1, 2:1 mole ratio. Number of moles of gases, if you recall, is equivalent to the volume for gases only, right? So since it is 2:1, it will mean that twice the number of moles of H2 is discharged compared to O2. So end of the day, you will have double the volume of H2 compared to O2. So take note, you must use the term double or twice here, because from the overall reaction, we can say that it is 2:1. We can say definitively that it is 2:1. So you must use the word twice or double here. Okay, new area here. Electrolysis of aqueous copper 2 sulfate using carbon electrodes. Just now we covered electrolysis of NaCl aqueous, we covered electrolysis of dilute sulfuric acid, and they were both with inert electrodes, carbon and graphite. So now let's go into the topic a little bit deeper. We will talk about the nature of the electrodes in this case. So before we compare a reactive electrode, let's start with the inert electrode first, and we see what happens. So we know that carbon or graphite is an inert electrode. So in the electrolysis of copper 2 sulfate solution, Cu2 plus Aq, CuSO4 Aq, we have Cu2 plus and SO4 2 minus, we have H plus and OH minus. At the cathode, H plus and Cu2 plus migrates to the cathode. They both migrate to the cathode. And we know that Cu2 plus is preferentially discharged compared to H plus. Why? If you recall the series, it is H plus, Cu2 plus, Ag plus. So Cu2 plus is more readily discharged or preferentially discharged compared to H plus. So at the cathode, what happens? We have copper solid forming around the cathode. Okay, let me see whether I can get a blank screen here. So back to this question. Cu2 plus is preferentially discharged as copper versus H plus. So what actually happens here? Imagine this. You have your electrode, negative terminal, positive terminal. This is the electrode. And you have your solution. The solution contains CuSO4Aq. So we know that Cu2 plus is preferentially discharged here. Is preferentially discharged as copper metal here. So when the copper metal is formed, it actually forms a layer around the electrode. So if you think about this, wouldn't this be similar to electroplating? So what happens during the reaction is that what happens during the electrolysis process is that the copper forms a layer around the electrode. So if we were to replace this electrode with something, so say for example, replace this with a piece of iron, the iron would become copper plated at the end of the day, right? Okay, let's move on to the anode. So anode, it's pretty simple. There are two ions here, SO4 2 minus and OH minus. So SO4 2 minus way high in the series, OH minus way at the bottom. So OH minus will always be preferentially discharged compared to SO4 2 minus. And we get H2O and O2 gas. So this remains in the solution. So what happens end of the day? As I mentioned earlier, the copper metal is discharged. It forms a layer around the cathode. The Cu2 plus concentration now, it decreases. So let's take a quick look. Imagine you have this solution here and you have a cathode here which copper is deposited continuously. So Cu2 plus is discharged here to give you Cu. Where does this Cu2 plus come from? There's a solution here. And this solution is CuSO4AQ. So Cu2 plus would be from the CuSO4 which you use to make the solution. And as the Cu2 plus is deposited around the cathode, the concentration of Cu2 plus in the solution will actually start dropping. So you will drop and drop and drop. So if you remember the color of copper 2 sulfate, this color is blue, correct? It's blue. So as the con of Cu2 plus drops, the blue solution will actually fade. It will fade. Or the blue color, or you can say that the blue color becomes less intense. So essentially it becomes lighter in color. Why? Because it is not being replenished. So intensity of the color decreases. But is there a way for us to ensure that the Cu2 plus concentration does not decrease? In fact, there is a way, and we just have to change the electrode. So let's take a look now. Earlier we used graphite as the electrode. Now we are using copper. So graphite is what we call inert. It is used to make an inert electrode. Copper in this case behaves like a reactive electrode. So why is it reactive? If you look at this diagram here, you notice that the copper anode here appears to be a bit smaller here. Seemingly it has dissolved during this reaction. So this is how it plays a part in the reaction. So let's analyze the question again. So let's start with the ions. You have Cu2 plus and SO4 2 minus, H plus and OH minus, still the same. Ions are unchanged. At the cathode, what happens? At the cathode, you have H plus and Cu2 plus ions which migrate to the cathode. And at the cathode, reduction occurs. Reduction occurs at the cathode. Cu2 plus is preferentially discharged. It's lower in the series compared to H plus. It is lower, so this is preferentially discharged. And it is discharged as copper solid. So we do not need to consider the nature of the electrode for cathode. Why? Because the cathode is copper metal, and we know that at the cathode, reduction occurs. Okay, reduction occurs. So can you reduce copper metal into, say, copper minus 1 or copper minus 2? No, it's not possible. So we ignore the nature of the electrode for the cathode and we focus on the ions present in the solution. Okay, in the solution. So copper in this case is discharged. Cu2 plus is discharged as Cu metal. Okay, at the anode is a bit different now. So if we analyze the ions, we know that SO4 2 minus, OH minus are present. Both of them will migrate to the electrode, and SO4 2 minus being at the top and OH minus being at the bottom of the series, OH minus will actually be preferentially discharged. However, in this case, you have a copper anode here, and copper behaves like a reactive electrode. So instead of OH minus being oxidized into O2 and H2O, the copper electrode itself is oxidized to Cu2 plus ions. Okay, so it is oxidized to Cu2 plus ions. SO4 2 minus and OH minus, they stay in solution. So if you think about this, what actually happens? What actually happens? So if I have this solution here now, I have copper. I have copper here. So this is the cathode. This is the anode. Okay, so cations are attracted to the cathode. Solution here is CuSO4Aq. My Cu2 plus ions comes here. They are reduced, becomes copper metal, deposited around this electrode here. And this anode here, the copper actually dissolves. So the copper dissolves to give me Cu2 plus ions. So after some time, it will become smaller and smaller and smaller, and then poof, it will disappear, and then reaction will stop. So if you think about this, earlier, if we imagine that this is not copper, there will be no copper metal being oxidized to Cu2 plus. So as a result, the Cu2 plus con in the solution, which actually comes from this copper sulfate used initially, will drop. But in this case here, when the Cu2 plus is discharged to the cathode, over at the anode side, it is actually being replenished. So if we think about this as in a cycle, the copper anode is oxidized to Cu2 plus. The Cu2 plus goes into the solution. The solution Cu2 plus is discharged at the cathode. So end of the day, one out, one in, one out, one in, one out, one in. The net will be 0. So there's no net change in the concentration of Cu2 plus. So effectively, by using a copper anode, I put in place a process to continuously replenish the Cu2 plus in the electrolyte. So if I summarize this now, we know that the copper anode will dissolve, it will decrease in mass. The con of the Cu2 plus remains unchanged because the Cu2 plus from the anode continuously replenishes the Cu2 plus that has been deposited on the cathode as copper. So it means that at the end of the reaction, we will expect to see that the intensity of the blue color remains unchanged. So if it was blue, it will be blue. If it was light blue, it will be light blue. So it will stay the same. It will not change. Okay, so this is how we replenish the ions that has been displaced at the cathode. So now let's move on to checkpoint 4. Pause the video here now to attempt the checkpoint. Continue the video once you are done. Let's move on to checkpoint 4 now. So checkpoint 4 is actually a very unique question. This is what we call a jackpot question because many students who attempt this question in O-levels will probably not get most of it correct. Okay, so there's a little graph here. Don't read too much into the numbers here first. So let's take a look at what the question is trying to present to us here. It is a semi-database sort of question. They give data here, here, and here. So we need to analyze the data to better answer the question. So let's take a look. This is aqueous copper 2 sulfate 2dm cube. The current, don't need to worry about this. But the mass here, let's take a look. It increases until it hits a plateau at 0.6 grams. Total mass of copper deposited on the cathode is 0.6 grams. So let's attempt the first question. Part A, write the ionic equations to represent the formation of copper and oxygen at the respective electrodes. Very simple. Cu2 plus to Cu solid. Anode is OH minus to O2 and H2O. Part B. So the question says that initially the solution contained 25 grams of copper 2 sulfate crystals, and they even gave you CuSO4.5H2O. So when you calculate the number of moles of copper 2 sulfate crystals, there is a need to include in the 5 times 18, which is the molar mass of water. So what is the initial concentration of copper 2 sulfate solution? Very easy. First step, we take the mass divided by the molar mass of copper 2 sulfate. crystals, we get 0.100 moles, and we know that the volume of the solution is 2 dm cubed. So con being number of moles divided by volume, we will have 0.0500 moles per dm cubed. Take note, all answers to 3SF, right? All to 3SF. The next part, this is the part which will lead on to the more interesting bits at the back. So from the graph, what is the mass of copper deposited after 10 minutes? So let's take a look. 10 minutes. 10 minutes. 10 minutes is here, so it would be around here, this region here. So it is 0.180 grams. So what is the number of moles of copper? It will be number of moles of copper equals to 0.180 divided by 64. And if I'm not wrong, it gives you, let me see, 0.00281. 0.00281 moles. Okay, so this value here will actually lead on to the next question. It is quite crucial that you get this value correct, 0.00281 moles. So now the question is asking you what is the concentration of copper 2 sulfate solution after 10 minutes. So after 10 minutes, how do you calculate what is the con? So let's think about this. Copper 2 sulfate solution, it gives you 1 mole per 1 mole, and because the Cu2 plus which is deposited comes from this Cu, this is also 1, so it's 1:1:1. So this is the first crucial step, and we know that at 10 minutes we have 0.180 grams or 0.00281 moles of copper deposited. So if we work backwards, we will know that 0.00281 moles of copper 2 sulfate solution, copper 2 sulfate has been deposited, has been lost because the copper has come out, it has deposited itself onto the electrode. So with this, we will now be able to calculate what is the mass or what is the number of moles of copper 2 sulfate that is left in the electrolyte. So let's take a look at how do we count this. So step 1, we must find the mass of copper deposited. This is what we know already from the graph. Number of moles we also know. And now this is the crucial step to equate. So we know that initially when there's 25 grams of copper 2 sulfate, it is 0.100. So now we have lost 0.00281. So this is the number of moles of copper 2 sulfate left. And the volume of water remains at 2 dm cubed. It remains literally unchanged. It's almost unchanged because it is 2 dm cubed. It is a huge volume, about 2000 cm cubed. So even losing a couple of cm cubed, we can assume that it still remains at 2 dm cubed. So the concentration again is a simple calculation of number of moles divided by volume, and we get 0.0486. So compared to the initial concentration of 0.0500 moles per dm cubed, we see that it has dropped very, very slightly after 10 minutes. So part 4 of the question, if I were to replace the electrodes by copper electrodes, what would be the concentration after 10 minutes? So recall, copper electrodes are reactive electrodes. Copper electrodes are reactive electrodes. So what happens? Remember, when the copper electrode is in the solution, the Cu solid becomes Cu2 plus and it replaces the Cu2 plus that is in the solution. So at the end of the day, the con will remain unchanged because it is continuously replenished by the copper anode. Okay, it is continuously replenished by the copper from the copper anode. So no change. So if I were to ask you about the color of the solution after 10 minutes, you can say that the intensity of the blue solution remains unchanged. Okay, intensity of the color of the blue solution remains unchanged. So now if we go back to using platinum electrodes, which we call inert electrodes, after 5 minutes, after 40 minutes, what happens? So we know that as the time progresses, the Cu2 plus will be discharged as Cu solid metal on the cathode, And as a result, the con of Cu2 plus will actually decrease. So after 5 minutes and after 40 minutes, what happens? So now let's refer back to the graph on the first page, on the first part of the question. We see that at 5 minutes, here, so much copper has come out. At 40 minutes, so much copper has come out. Okay, so take note, 0.6 and probably about 0.1 grams of copper here. So we know that as time progresses, the color of the solution will actually fade. It will fade and fade and fade and fade and fade until this point here in time, which is about 32 minutes. Then the intensity of the color will remain the same because no additional copper 2 plus ions have been discharged as copper. So now, the crucial part here is recognizing the fact that this is 0.6 grams of copper that has been deposited. So if you look at this question again, we know that we have 25 grams of copper 2 sulfate crystals. Okay, and this translates to 0.100 moles of CuSO4.5H2O. And this translates to 0.100 moles of copper. So what is the total mass of copper that is present in this solution? The mass is number of moles, number of moles times molar mass, and we get 6.4 grams. So the total mass of copper present is 6.4 grams, of which at 5 minutes, only 0.1 gram was discharged, and at 40 minutes, only 0.6 grams was discharged. So it means that at the end of the day, there is still a lot of Cu2 plus present in the solution. So at no point in time will the solution become colorless. So we can make this deduction because the graph is given to us. So if there's no graph given to us, we will assume that after a long period of time, all the Cu2 plus will actually be deposited. They will all come out as Cu solid, and the solution will become colorless. But in this case, because the graph tells us that it is not so, only 0.1 and 0.6 grams of copper came out at 5 and 40 minutes. It means that the solution simply fades in color. It only fades in color. So at 5 minutes, it will be a lighter shade of blue. At 5 minutes, it will be a lighter shade of blue. At 5 minutes, lighter shade of blue. And at 40 minutes, it is still blue, but it is again a lighter shade of blue than the original solution. But we know that it is the same shade of blue as the solution at 32 minutes, because from the 32-minute mark onwards, there was no more additional copper deposited on the electrode. Okay, so this part, please look through again if you're not very clear. Rewind the video and watch again. Look through the analysis and be very clear as to why I have come to this conclusion that it still remains blue at both time periods, even though the copper, the graph initially shows a plateau. Okay, 0.6 grams versus 6.4 grams maximum possible deposition. Part D of the question is quite simple. So why does the mass of copper not increase after 32 minutes? We know that we have 6.4 grams of copper that could possibly come out, but only 0.6 grams was discharged. So why did the copper stop coming out? It is actually because the concentration of the Cu2 plus ions has decreased. So you recall earlier, there was this thing when we mentioned there were 4 different areas which affects what ions, what substances are discharged. Cation, the anion, the concentration, and the nature of the electrode. So in this case, the concentration factor has come into play. So Cu2 plus con has dropped. So it has dropped below the point at which it can be discharged. So if you recall the series, it is H plus, Cu2 plus, Ag plus. So if Cu2 plus con has decreased so much that it cannot be deposited, it cannot be discharged at the cathode, the next ion which will be discharged there will be the H plus ion. And H plus ion will be discharged as hydrogen gas. Okay? The last question here, don't read too much into this. So theoretically 0.64 grams of copper should have been deposited after 32 minutes. 0.64 grams here, if you recall, earlier calculation was supposed to be 6.4 grams. So, but if you link it to the previous question, all 6.4 grams will never come out because the con will actually drop and it will stop the reaction. Okay, it will stop the deposition of Cu2 plus as Cu on the cathode. So, based on calculations, based on some calculated values, we know that 0.64 grams should come out, but only 0.6 grams was discharged and deposited after 32 minutes. So we have a difference of 0.04 grams of copper. So why is this so? Suggest the reason. So electrolysis, if you recall, involves the decomposition of a substance by electricity. So in order for electricity to flow, the conductivity or the resistance of the solution must be quite low. So as more and more copper 2 plus ions were deposited, at the end of the day, the resistance of the solution will actually increase, or I can say that the conductivity decreases. So as a result, resistance increases, the whole process will actually stop. The other factor is because if you recall the picture, a copper layer actually coats the cathode. So a layer coats around the cathode, and this coating, as you can see, even from the way I draw it, it cannot be 100% perfect. So if it is not a perfect layer, it means that the resistance at the electrode will actually increase. Okay, the resistance at the electrode will actually increase. It is not a perfect coating of copper. So after some time, the resistance increases, it prevents it from conducting as well, so it attracts less Cu2 plus ions, and at the end of the day, it means that less copper will be deposited. Okay? Now let's take a moment to look through what you have just learned. Flip through your notes, look through the content, recall the questions, try the questions again, get yourself familiarized first before we move on to the next big section in electrolysis. The next major part of electrolysis is actually the industrial applications of electrolysis. So we are covering two things here. One is the purification of metals and one is electroplating. So in fact, as we went through the earlier scenarios of the different electrolytic cells, we have already covered these two things. But now let's put a context to what we have covered. So we start with the purification of metals. So you recall this diagram from earlier, where electrolyzed copper 2 sulfate solution with copper electrodes. So copper being a reactive electrode, it dissolves. So if you imagine this, if the copper anode here contains copper plus other junk, okay, alright. So all these other substances, which I call junk, will actually fall off the electrode and collect below the anode. There's a term for this actually, it is called anode sludge. S-L-U-D-G-E, anode sludge. So this is basically the waste materials. So if I have a copper anode here, which contains impurities. So only my Cu2 plus will enter the solution. And it will be deposited over at the cathode as copper metal. So if you think about this, as the process continues, it means that this anode will actually start dissolving. Only pure copper can become Cu2 plus, because only Cu can become Cu2 plus. So Cu2 plus will travel in the electrolyte over to the cathode and be reduced to form Cu on the cathode here. So effectively what I have done is basically is that I've extracted the pure copper from this impure anode and transferred it over to the pure cathode. So if I used pure copper as the cathode, at the end of the day, what I will get is a very thick block of pure copper. So I've effectively purified the impure anode. The next thing of electrolysis is electroplating. So if you look around yourself, every day when you go to the toilet, you use the taps. The taps look a bit silver, shiny color. So in fact, the taps are what we call chromium plated. Usually below the nice shiny chromium layer is actually the raw material used to make the taps. Most of the time they use copper because copper is quite cheap. And because copper doesn't really look appealing, the color is not really that nice, they coat it or they electroplate it with a layer of chromium to make it look nice and presentable and attractive so they can sell it for more money. So how does electroplating work? Very simple. So if you think about this, earlier copper 2 plus ions will deposit itself on the cathode. So if I were to replace the cathode with the object, it will mean that the copper 2 plus ions will actually be preferentially discharged at the cathode, and the cathode is the object to be plated, so it will form one layer around the object. And voila, we have electroplating. In this case, we call this copper plating because it is copper metal which is deposited on the object. So at the anode, what happens? The anode here is copper. So the copper anode will dissolve. It will give you Cu2 plus. And this Cu2 plus enters into the solution and migrates over to the cathode and becomes deposited as copper here. So the concentration of Cu2 plus in the solution remains unchanged. So this process can continue non-stop. So you just need to keep dipping in your object. Dip, take out, dip, take out, dip, take out. And you repeat this process on and on and on until the copper block here, the copper anode here, is completely gone. Then you replace this and you can continue the process again and again. So with this, let's move on to checkpoint 5. Pause the video now to attempt the checkpoint. Continue with the video once you are done. Now let's move on to checkpoint 5. So this is a very simple setup here which can be used to chromium plate an object. So if you recall from earlier we used copper here, and this was copper 2 sulfate solution, and we copper plated the object. So in this case now we are trying to chromium plate this object. So we replace the electrolyte with chromium 3 sulfate, and we replace the metal here with chromium, so the chromium can continuously replenish the Cr3 plus which was deposited on the object. Okay, so which is the positive and negative sign to the power source? It's pretty simple. For the Cr3 plus to be attracted here, this has to be the negative and this has to be the positive. So what happens to the electrolyte and the chromium metal? So as mentioned earlier, the Cr metal here will actually continuously replace the Cr3 plus in the electrolyte. The Cr3 plus will be deposited on the object here. So at the end of the day, the concentration of Cr3 plus in the solution will remain unchanged, but this chromium electrode here will gradually dissolve. So its mass will gradually decrease as well. Okay, so color intensity remains unchanged, but the chromium metal will decrease in mass as it is oxidized to Cr3 plus ions which enter into the electrolyte. So the anode becomes oxidized. So just one reason why chromium plating is used. I mentioned this earlier just now. So the taps in our toilets are chromium plated for a few reasons. One of which is to make it look more attractive. Sometimes chromium is used to coat metal objects such as iron fenders of cars and iron fenders of jeeps, also to give it a more attractive appearance. Because you could probably make the tap out of out of 100% chromium, maybe the tap will cost you upwards from $500. Not very sure. It'll be pretty expensive because chromium is not exactly very cheap. But if we chromium plate a copper tap, the tap can be sold to you for a couple of tens of bucks. So two reasons. One is to make the surfaces of objects more attractive, and it can also help prevent rusting. Take note, rusting only applies to iron-based objects because rust is hydrated iron 3 oxide, Fe2O 3.xH2O. This is iron. So rusting is only for iron-based objects. In most cases, it is used to make the objects look more attractive and presentable. Okay, the last part of the electrolysis notes or chapter actually brings us to this thing which we call the simple cell. So let's start with a very simple definition first. A simple cell converts chemical energy into electrical energy. So I'm pretty sure you would have used some simple cells before in your whole life. You know this little thing which we call a battery. This is what we call a battery. In fact, the word batteries has been wrongly used by many people because by itself, this is supposed to be called a cell. A cell. So the different brands, Energizer, Duracell, Panasonic, GP, so on and so forth, all these are called cells. Okay, all these are called cells, and only when they are connected together in a circuit and used to power something, say a light bulb, this is what we call a battery. By itself, this is cell 1, this is cell 2, these two together is called a battery. So how does a simple cell work? Let's take a look. So we start with a very simple zinc copper cell, electrolyte being dilute sulfuric acid. And from this diagram here, we see that the electrons flow from the zinc electrode over to the copper electrode. So why is this so? And how do we know this happens? So if you think a bit more deeply, you will realize that the two electrodes here are made of different metals, zinc and copper. And in the reactivity series, if you recall, zinc is way higher than copper in the series. So what does this mean? If we make an initial deduction from this, we can probably guess that because electrons have to flow from zinc over to copper, it means that the zinc electrode is actually releasing the electrons. So how does Zn release electrons? It must form something else. So what is this something else? Let's take a look. So first of all, we have zinc and copper. We must first identify which electrode is oxidized. And because one is oxidized, reduction will happen at the other electrode. So in this case, the more reactive metal here will be oxidized. So in this case, it is Zn. Zn is the more reactive metal, it is oxidized. So when it is oxidized, what does it form? Zinc is oxidized to Zn2 plus 2 electrons. So you can see for now that the electrons come from the oxidation of zinc. And what happens to these electrons? They flow one round over to the other electrode. In this case, it's copper. So as you can see, zinc oxidized to Zn2+, loses 2 electrons per zinc atom. So because it contributes the electrons, it behaves as a negative electrode. The negative electrode. Okay? The zinc ions enter into the solution. They go into the electrolyte. But the electrons travel one round. They travel one round. Okay, one round to the copper electrode. So as it goes over to the copper electrode, what happens at the copper electrode? The copper electrode is in contact with H plus ions in the acid. So H plus ions accept the electrons and is reduced to form hydrogen gas. So if you recall from the earlier part, copper can sometimes behave like a reactive electrode, but it is not possible for the copper to accept an electron to form Cu minus. This is impossible. So the next thing which can happen is to the ions that surround the copper electrode. So in this case, it is H plus ions. The H plus ions gain electrons to give you H2. So overall, when you combine them together, this is what you get. And before we move on to the next cell, let me illustrate to you a very simple example which we see every day, but maybe we never think much about it. So, do you remember just now I mentioned about the usual batteries, which we always the usual cells we always call batteries? So maybe let's say this is a typical simple cell, and it gives us 1.5 volts. You know, the 1.5 volts double A, triple A, D, C, etc. kind of batteries or kind of cells. So if you haven't had this, if you haven't had a chance to do this before, maybe you can try this over the holidays or when you are free. Look for cells which are made in Singapore and contain 0% mercury, 0% cadmium, and 0%, let me see, mercury, cadmium, and 0% lead. Yes, lead. Because these three substances are extremely toxic for what's going to happen later on. So buy a good battery, a good cell without these three toxic substances, and we will now proceed, and you can now proceed to dismantle the cell. So how do you go about doing this? So first step, around the cell, usually there is always a plastic layer. So use a penknife, make a mark down and rip off the plastic layer. So once the plastic layer goes off, you will see the cell below, and you will see a shiny casing which makes up the large part of the body of the cell. So now the next thing you need to do is to use a pair of pliers, and you grab the top of the cell or the bottom, depending on where the notch is. Grab the top or bottom of the cell, and then you give it a real hard twist. So if you do this properly, the top part of the cell will actually come off, and you can pull it out, and you will see something like this. Okay, so this is the casing of the cell, and you will see a long black color stick here, which is the electrode. So how does dismantling this simple cell tell you more, or tell us more about how it works? First things first, let me tell you, the casing is actually made of zinc. The casing is made of zinc, and this electrode here is actually graphite. This is a graphite or carbon electrode. So based on what you learned earlier, you will know that zinc will be preferentially oxidized. So zinc is oxidized to Zn2 plus 2 electrons. So think about this a little bit more. The bottom of the battery or bottom of the cell is the negative terminal of the cell. So the negative terminal is because electrons are produced here. So electrons flow one round into your circuit and flow back into the positive terminal, which is now the graphite. So this part here is a paste. The paste contains the electrolyte. The electrolyte could be a acidic solution. It actually depends on what the manufacturers use. So there will be H plus ions present, and if you recall the earlier diagram, H plus ions will be reduced to H2 gas. So this completes the cycle. Electrons are produced by the zinc casing. They flow one round, they go back to the graphite electrode here, which is the positive terminal of the simple cell. And because H2 gas is produced, so you will think about this. If I were to keep producing H2 gas continuously, after some time, it will mean that there will be a buildup of gas within the cell, and the cell will probably explode. So how do you prevent the cell from exploding? As you are dismantling the cell, if you examine it very carefully, you may be able to see tiny vents at the top or at the bottom of the cell. So the vents here are to allow the H2 gas to escape, so the cell wouldn't bloat and explode as you use them. Okay, so if you haven't had the chance to do this over the holidays, buy a good cell and have a good time, and try to get a hang of dismantling the cell and to see what's inside the cell. Okay, so now let's move on to a next simple cell. This one is a bit more unique. So earlier we used H2SO4. Now we are using copper 2 sulfate, but the electrodes remain the same. So essentially everything occurs in the same way, except that over here, instead of H plus being discharged as H2 gas, we now have Cu2 plus present in the solution, and this Cu2 plus will be discharged as copper solid. Why? If you recall the series, H plus, Cu2 plus, Ag plus. So ease of discharge increases down the series. So Cu2 plus will be preferentially discharged compared to the H plus ion. So let's take a closer look again. First things, zinc, copper is the same. Zinc is oxidized because it is more reactive. So this is the negative electrode. Negative electrode. The electrons flow one round. They travel from the zinc to the copper electrode. And as I mentioned earlier, the solution contains both Cu2 plus and H plus ions. And Cu2 plus is more easily discharged. So as a result, the Cu2 plus accepts the electrons and it forms copper, and this copper coats around the electrode. Alright. So just now when I talked about the simple cell you use in your daily life is about 1. So how do we get the different voltages? It all depends on the difference in the reactivities between the two metals used. So zinc copper gives you 1.1 volts. The bigger the difference between the reactivities of the metals, the larger the voltage we get from the simple cell. So now let's move on to the last checkpoint. Pause the video now to attempt the checkpoint. Continue with the video once you are done. So for question 1, this is the simple diagram here. You notice that this power source is connected to 4 different electrolytic cells. So in which cell is the intensity, the blue color, unchanged? So they all contain aqueous copper 2 sulfate, which means that the Cu2 plus will be deposited as Cu solid at the cathode. And if there's no replenishment, of the Cu2 plus at the anode, the blue color will slowly fade. So if we take a look here, this one and this one, cells W and X have platinum electrodes here. They have platinum anodes here. It is impossible to replace the Cu2 plus with platinum electrodes. So at the end of the day, in these two solutions here, the blue color intensity will actually decrease. Y and Z, they have copper electrodes here, which will continuously replace the Cu2 plus in the solution. So the color remains unchanged. Answer is Y and Z. For question 2, why does the mass of Q increase more than that of S? There are 4 possible options here. So if we were to analyze the options one by one, we will know that D is not feasible. Alright, for question 2, why is the increase in mass of Q greater than that of S? If we were to analyze the 4 options here, we will know that D is not possible because D is talking about P and R. So why does the mass of electrode Q increase more than S? If we were to take a closer look, Q and S are both connected to the negative terminal of the power source, which means that the cations will migrate there and be discharged. So in order for the mass of Q to increase more than that of S, it means that the metal that's deposited on Q must be heavier than that deposited at S. So if we look through the options here, we will see that the answer is A. The cations are different in the two cells here. So in cell 1, it is a heavier cation. In cell 2, it is a lighter cation. So as a result, when the cation is deposited at the electrode, Q increases, the mass of Q increases more than that of S. Question 3 is a pretty interesting question. So we see that there's silver nitrate here and there is potassium iodide here. So if we were to break down the question, Ag plus, NO3 minus, H plus, OH minus at this side, K plus, I minus, H plus, and OH minus at this side. This is the positive terminal, this is the negative terminal. It means that my Ag plus will migrate over to here, my NO3 will remain here, my H plus will migrate over to here, my OH minus will remain here. So for at this side, K plus, K plus will migrate over, K plus will stay here, I minus will migrate over to the anode, H plus will stay here, OH minus will migrate over to the anode. So based on this analysis, we can determine what is this pale yellow streak here. So let's take a quick look. So what are the ions present in the solutions? We have Ag plus NO3 minus for the silver nitrate solution, K plus I minus for the potassium iodide solution. So what is the pale yellow streak here? As mentioned earlier, Ag plus migrates over, I minus migrates over, somewhere along they meet, Ag plus reacts with I minus, and it gives you your AgI, silver iodide. This is a yellow precipitate. Recall from QA, silver chloride is white in color, silver bromide is pale yellow, and silver iodide is yellow in color. So, how do you explain the process leading to the formation of the streak, and why does it appear nearer the cathode than the anode? If you see, it is nearer the cathode than the anode. It is over here, it is not in the middle. So why is that so? If you recall, earlier last year, in the earlier topic, there is this question of NH3 and HCl, and they form a white band somewhere 1/3 of the position away from NH3. Sorry, should be HCl. This should be correct. This is correct. NH3 and HCl. So why does the white band form nearer to HCl compared to NH3? So in this question, remember, NH3 molar mass is 14 plus 3 equals to 17. This is 1 plus 35.5 equals to 36.5. So we can see from this that actually the molar mass of HCl is double that of NH3. So as a result, it migrates slower, and the band forms nearer to the HCl. So similarly to this question, we know that both Ag plus and H plus migrates to the cathode. We know that I minus OH minus migrates to the anode, and somewhere along the way, Ag plus and I minus, they meet and they react to give you AgI, which is the yellow streak, and Ag plus has a relative ionic mass of 108 versus I minus 127. So I minus is actually heavier than Ag plus. So as a result, Ag plus migrates faster than I minus, and the yellow streak forms nearer towards the I minus, the side where I minus is, which is the cathode. Alright, so with this, we have come to the end of the electrolysis topic. So look through your notes again and attempt the questions if you are still not clear about the topic, still not clear about what are the different concepts required. Try in particular the areas where we analyze concentrated and dilute solutions, because this involves some concepts which you will need to be very clear about to do the questions well. So other than that, you can try the tutorials. The answers for the tutorials are provided, and thank you.